Hi everyone, my name is Julian Samaroo. I'm the author of BPFnative.jl, the Julia package for everything BPF related. I've been working on BPF Native in tandem with my HPC work at the MIT Julia Lab, and would like to thank the lab as well as Valentin Sharafi for supporting and mentoring me in this endeavor. What is BPF? BPF is a virtual machine and instruction set originally designed for BSD operating systems and ported to Linux. BPF in the Linux kernel was extended to a more extensive architecture termed Extended BPF, or eBPF, which better maps to modern CPU hardware. The focus of this talk will be on eBPF, which I will just refer to as BPF for simplicity. Where is BPF? BPF is located in every semi-recent Linux kernel in the world today as an in-kernel programming interface. BPF also exists in a number of user space implementations, such as uBPF and generic eBPF. BPF is even being integrated into Windows via the eBPF for Windows project. What can I do with BPF? Most importantly, BPF on Linux unleashes superpowers for Linux users. BPF is used for network packet filtering, security-focused isolation and auditing of user processes, introspection and observability of kernel processes, performance monitoring, user space probing, and so much more. BPF is the multi-tool that lets basically anyone write kernel code from the safety of user space. So how can this be safe? Isn't writing kernel code dangerous? Not so with BPF. The Linux kernel includes a verifier that is run on any BPF program loaded into the kernel. If the verifier can't prove that the program terminates in fixed time, accesses memory safely, and only uses allowed functionality, the program is rejected. This is far safer than the alternative of writing a kernel module in C, which is only as safe as the developer is careful. So as a Julia user on a Linux system, why should I care? Isn't BPF usually written in C? Here's where BPF Native comes into the picture. BPF Native lets Julia users write BPF programs in pure Julia, no C required. With BPF Native, anything you can do with C, you can do in Julia instead for BPF. BPF Native goes further than that too. It binds to the libbpf library, which makes loading BPF programs into the kernel easy. BPF Native exposes the BPF user space API via idiomatic Julia functions and tries to make BPF kernel programming as idiomatic as possible. Hopefully you're now convinced that BPF and BPF Native are somewhat interesting, but let's now drive the point home with some real useful examples. Let's start off with something simple. Let's add a BPF probe to the write system call that prints which process is doing the writing. So this program is pretty simple. We load BPF Native and some relevant modules. We create what's called a kprobe, or a kernel function probe, and we put it on the cases write call, which is just the function which is called when a write system call is invoked, and we make it GPL licensed. Now this is necessary because certain BPF functions can only be used from GPL programs, so we declare this as a GPL program. Now we have a kind of funky syntax in here for creating a string. I'll discuss that at the end. And we make it hello world, so very simple. And now we want to go ahead and just print something out, the canonical example. So what we do is we invoke this traceprintk call from the RT module, or runtime module. And this is a printf compatible function. If you've used C or C++ or Julia's printf standard library, you'd be familiar with this. And it prints out the FMT or format string, which will just print hello world, but we can also accept arguments for this if you modify your format string. Now, if you've done any GPU kernel programming, you'll maybe be a little bit confused because we're actually returning a value here. Unlike GPU kernel programming, we actually do return a integer value from BPF programs. And in this case, we're just returning 0 to indicate nothing special happened, all is well. But we can return other values to indicate an error, invoke some other action. Now, when we run this, what's going to happen is that this BPF program will be attached to the cases write function within the Linux kernel that I'm running right now, and anytime the write system call is invoked, our BPF program will get run. And so we can actually see the results of this if we look at the trace pipe, which is a debugging file within Linux used for seeing these traceprintk calls. So here we see actually a lot of activity going on from cat and from a PTY reader process, and we see our hello world getting printed out. So great, this is just as we'd expect. So we can hook into kernel functions and see which process caused them to execute. So you've surely noticed the funky macro for allocating strings. This is necessary since regular Julia strings don't work well when compiled to BPF, so we swap them out for something more compatible. So if BPF runs isolated in the kernel, can we still talk to Julia from a BPF program in a more structured manner than printing to some pipe? Yes, BPF has the concept of what's called maps, which are regions of memory shared between the kernel and user space. BPF Native makes it trivial to allocate maps and access them from Julia using the familiar array and dictionary interfaces. So we can see here that we allocate a map called mymap using the rtmap function, and it's a hash map, so a dictionary. And it has key and value types of int, so this is like a dict of int. And something kind of unique is that it has a max number of entries. So unlike a Julia dictionary, all BPF maps have a max size, and you need to declare that ahead of time so that you don't accidentally use an infinite amount of memory. Now, the rest of this is pretty simple, and we have a kprobe on the write system call just as before, and all we do is we write into our map at the key 42, we write the value 4242. Very simple. I'm sure everyone has seen the syntax before. It's the same as dictionary array indexing syntax. So we can go ahead and load this into the kernel, and what we can do is while it's running, we can access it. We can access the map with host.hostmap call, which gets a host side handle to our map that we've created in the kernel. That's being written from our BPF program right now. And what we can do is we can query it and say, hey, do we have the key 42? Yes, we do. Do we have the key 43? Of course we don't. We didn't write there. And then if we actually print that out, print out the map at index 42, we get the value 4242 as we would expect if our program was running, which it is. So great. So let's now tie together everything that we know about BPF and BPF native and do something really fancy. So let's port the excellent off wake time tool written by Netflix's BPF wizard Brendan Gregg to BPF native to check out what our Linux system is doing. So what this tool does, when you're looking at processes and what they do, much of what they do that spends time in the kernel is system calls. So a process does a write, does a read, does a network operation, and it does a system call to do that. And many of these system calls have to actually go and do something that takes a lot of time to complete. Say a write, when you do a write to a file, you actually need to wait for that write to hit the hard drive and then come back and say, yeah, I'm done. I've done that write. The disk now has this write. And so when we're waiting for that to happen, our process is put to sleep, and a kernel thread might be operating, doing something, doing the write. When it's done, that kernel thread will come back to our process and wake up our Julia process, and then it will be able to continue executing. So we have this tool running right now, and what we have is a simple rendering of what's going on, what processes are doing things, and which kernel thread or other thread is causing the system calls invoked by our process to complete. This is a slightly more complicated stack trace we have right here, but it looks like Julia is doing a read, and this is actually waking up a thread, a GFX thread, which is probably just a kernel GPU rendering thread, as a result of its read. So maybe the graphics processor was doing some sort of write to Julia, and Julia's read finalized that, allowed it to wake back up. And you can see this happen in both ways, where the kernel wakes up user space wakes up the kernel, and all other various combinations of that. So with this tool, we can see why processes are put to sleep by the kernel and which other processes woke them back up. This is the sort of observability tool that's invaluable for debugging slowdowns and hangs in production systems, where more invasive introspection techniques can't be used, such as modifying the source code and recompiling. So you can imagine that tools like this, when ported to Julia, could be really powerful for sysadmin or for average users or developers in understanding what their system is doing. So that's all I've got time to share, but I'd love to see what ideas you people come up with. Please open issues on BPF Native if you find something that doesn't work or is unintuitive. I'm also very open to any contributions. Thanks so much, and I'm ready for any questions.